Welcome to today's paper reading. Today's paper is titled, Survey on Factuality in Large Language Models, Knowledge, Retrieval and Domain-Specificity. This paper, published in ACM Computing Surveys, surveys the factuality in large language models by Cunxiang Wang and colleagues from Westlake University, Jiayang University, and other esteemed institutions. The survey focuses on the critical issue of factuality in large language models, LLMs. The factuality issue is defined as the likelihood of LLMs producing content that is inconsistent with established facts. This inaccuracy can lead to significant consequences and challenges. The survey examines how LLMs store and process facts, identifying the main causes of factual errors. It also discusses methods for evaluating LLM factuality, including key metrics and benchmarks. Additionally, the survey explores strategies to enhance LLM factuality, particularly in specific domains. Two primary LLM configurations are highlighted: standalone LLMs and retrieval-augmented LLMs, each with unique challenges and potential enhancements. The historical context of AI development highlights seminal works by McCarthy et al. And Newell and Simon, emphasizing knowledge representation and reasoning. The SITE project aimed to codify common-sense knowledge. The emergence of large language models, LLMs, like ChatGPT and GPT-4 represents a significant leap in AI capabilities. However, these models also raise concerns about generating non-factual or misleading content. The factuality of LLMs is crucial for responsible use in various domains, including health, law, and finance, where incorrect information can lead to serious consequences. Figure 1 presents a comprehensive taxonomy of research focused on the factuality of large language models, LLMs. The taxonomy is divided into 4 main sections: the issue of factuality, evaluation methods, analysis of factuality mechanisms, and enhancement strategies. It highlights the distinction between standalone LLMs like ChatGPT and GPT-4, and retrieval-augmented LLMs such as BingChat, which utilize external data. The evaluation section covers various metrics and benchmarks used to assess LLM factuality, including rule-based, neural, human, and LLM-based evaluation metrics, as well as specific benchmarks like MLU and Truthful QA. The analysis section delves into the causes of factual errors at the model, retrieval, and inference levels. Finally, the enhancement section outlines strategies to improve factuality, including pre-training, supervised fine-tuning, multi-agent approaches, and domain-specific enhancements like HuaDuoGPT for medicine and LawGPT for law. Factuality in large language models refers to their ability to generate content that adheres to factual information. This includes common-sense knowledge, world knowledge, and domain-specific facts, all of which should be grounded in reliable sources like dictionaries, Wikipedia, or textbooks. However, several types of factual errors can occur. These include domain knowledge deficits, where the model lacks specific factual knowledge in areas like medicine or law. Outdated information is another issue, where the model provides information that has been superseded by more recent data. Reasoning errors occur when the model fails to correctly reason out the answer despite having the relevant facts. The impact of these factuality issues is significant. They can lead to societal and economic losses, as well as legal implications. For instance, a lawyer faced sanctions for submitting hallucinated case law in court, and a mayor in Australia discovered false claims made by ChatGPT about his personal convictions. These examples highlight the critical need for addressing factuality issues in large language models. Table 1 illustrates various types of factual errors produced by large language models, categorized by their causes. Model-level causes include domain knowledge deficits and outdated information, where the model lacks specific expertise or is unaware of recent updates. Retrieval-level causes involve issues with the data retrieval process, such as misinformation and distracting information that mislead the model. Inference-level causes pertain to errors during the generation process, including snowballing effects where minor initial errors compound, and exposure bias where the model's outputs reflect its training data rather than factual accuracy. Table 2 provides a detailed comparison between the factuality issue and the hallucination issue in large language models, LLMs. The table categorizes outputs into 4 distinct types: factual and non-hallucinated, non-factual and hallucinated, hallucinated but factual, and non-factual but non-hallucinated. Each category is defined by whether the output is factually correct and/or faithful to the prompt. For instance, factual and non-hallucinated outputs are entirely correct, while non-factual and hallucinated outputs are entirely fabricated. Hallucinated but factual outputs are unfaithful to the prompt but remain factually correct, and non-factual but non-hallucinated outputs avoid direct answers or provide incomplete but not hallucinated responses. This categorization helps in understanding the nuanced differences between factuality and hallucination in LLMs, which are crucial for assessing the accuracy and reliability of generated content. Table 3 provides a comprehensive overview of various evaluation metrics used to assess the factuality of large language models, LLMs. The metrics are categorized into rule-based, neural, human, and LLM-based evaluations. Rule-based metrics include exact match and common metrics like accuracy, precision, recall, and F-measure. Neural metrics such as ADAM, BRT score, and BLERT use machine learning models to evaluate the semantic alignment between generated and reference texts. Human evaluation metrics like attribution and FX score focus on the verifiability and accuracy of the generated content. LLM-based metrics, including GPT score and GPT judge, leverage the capabilities of other LLMs to evaluate the quality and truthfulness of generated texts. This table is crucial for understanding the diverse methods employed to ensure the reliability and accuracy of LLMs in generating factual content. The evaluation of factuality in large language models, LLMs, is crucial for ensuring the reliability and trustworthiness of the content they generate. As LLMs are increasingly integrated into various applications, the accuracy of their outputs becomes paramount. To assess the factuality of LLMs, several evaluation metrics and benchmarks are used. These metrics can be categorized into rule-based, neural, and human evaluation metrics. Prominent benchmarks include MLU, Truthful QA, HalloEval, Big Bench, CEval, and Self-Aware. Each of these benchmarks serves a specific purpose in evaluating the factuality of LLMs, from assessing multitask accuracy to understanding hallucination tendencies. Table 4 provides a comprehensive overview of benchmarks used to evaluate the factuality of large language models, LLMs. The table categorizes each benchmark by task type, lists associated subdatasets, specifies evaluation metrics, and presents the performance of select representative LLMs. Key benchmarks include MLU, which tests multitask accuracy across 57 diverse subjects, Truthful QA, designed to assess truthfulness in answers across 38 categories, and CEval, which evaluates advanced knowledge and reasoning abilities in a Chinese context across 52 disciplines with 4 levels of difficulty. These benchmarks are crucial for understanding and improving the factual accuracy of LLMs. Table 5 provides an overview of studies that focus on the evaluation of factuality in large language models, LLMs. It highlights whether these evaluations included human evaluation and specifies the granularity of the evaluation, distinguishing between token-level and sentence-level assessments. The table also lists various datasets and metrics used in these studies to measure the factuality of LLMs. This information is crucial for understanding the methodologies and results of factuality evaluations in LLMs. Table 6 provides a comprehensive list of benchmarks utilized in the enhancement of large language models, LLMs, with respect to factuality. The table categorizes these benchmarks based on whether they incorporate human evaluation, denoted by the human eval column. Additionally, it specifies the level of evaluation granularity, distinguishing between token-level, T, and sentence-level, S, assessments. This table is crucial for understanding the methodologies and tools employed to evaluate the factual accuracy of LLMs, ensuring their reliability and performance in various applications. Table 7 provides a comprehensive overview of benchmarks used for evaluating the factuality of large language models, LLMs, in various domains. The table details the specific domains, tasks, datasets, and the LLMs that have been evaluated in each study. For instance, in the finance domain, tasks such as sentiment analysis and stock movement prediction are evaluated using metrics like F1 and ACC. The table also lists the LLMs that have been tested, including Bloomberg GPT and GPT-4. In the medical domain, benchmarks like CMB and Huadao 26M are used to assess LLMs such as ChatGPT and Medical GPT. Each entry in the table offers a snapshot of how different LLMs perform in specialized tasks, providing valuable insights for researchers and practitioners in the field of LLMs. The analysis of factuality in large language models, LLMs, involves several key aspects. Firstly, knowledge storage. Research indicates that factual knowledge is primarily stored in the early layer feed-forward networks, FFNs, of LLMs. These layers are conceptualized as a query, keys, and values, with the intermediate hidden state representing activation values for each memory. Additionally, language-independent neurons have been found to express multilingual knowledge. Secondly, knowledge completeness. LLMs exhibit self-awareness and can discern their knowledge gaps. There is a dichotomy between parametric knowledge and retrieved knowledge, with LLMs often being overly confident about their responses. Retrieval enhancement can compensate for this shortcoming. Lastly, contextual influence. LLM's ability to utilize context is crucial. Larger models tend to rely on their parametric knowledge even when faced with counterfactual contexts. When confronted with conflicting information, models may default to their internal knowledge or exhibit a strong confirmation bias. The balance between controllability and robustness remains a challenge in LLM training. This slide outlines the primary methods to enhance factuality in large language models, LLMs. For standalone LLM generation, techniques include improving factual knowledge from unsupervised corpora, enhancing supervised data, and optimizing the elicitation of factual knowledge from the model. In retrieval augmented generation (RAG), the focus is on the normal RAG setting, interactive retrieval, and adapting LLMs to the RAG setting. Lastly, domain-specific factuality enhancement covers healthcare, legal, and finance LLMs, each tailored to their respective domains to ensure accurate and contextually relevant responses. Figure 2 provides an overview of methods to enhance factuality in large language models. The figure outlines 3 primary areas of focus: enhancement techniques for pure LLMs, strategies for retrieval-augmented LLMs, and methods employed by domain-specific LLMs to boost their factual accuracy within their respective domains. These methods are crucial for improving the reliability and accuracy of LLM outputs across various applications and industries. Table 8 presents a comprehensive summary of the performance metrics for selected factuality enhancement methods across various datasets. The table contrasts baseline models with their enhanced counterparts, showing improvements denoted by an arrow. It is important to note that due to space limitations, only a subset of datasets, metrics, and models from each research work is included. The table serves as a valuable resource for understanding the effectiveness of different enhancement strategies in improving the factuality of large language models. Key metrics such as exact match, EM, and accuracy, ACC, are highlighted, providing a clear comparison of how these methods perform relative to their baseline versions. Researchers and practitioners can use this data to inform their choices of enhancement methods based on specific dataset requirements and performance criteria. Table 9 presents a comprehensive overview of large language models, LLMs, that have been enhanced for domain-specific factuality. The domains covered include healthcare/medicine, H, finance, F, law/legal, L, geoscience/environment, G, education, E, food testing, FT, and home renovation, HR. Each entry in the table details the base model used, the evaluation task, the dataset employed, and whether the model underwent continual pre-training, continual supervised fine-tuning, SFT, training from scratch, or utilized external knowledge. This table serves as a valuable resource for understanding the specialized enhancements applied to LLMs to improve their performance and reliability in specific domains. The evaluation of factuality remains a complex challenge due to the inherent variability and nuances of natural languages. The core processes governing how LLMs store, update, and produce facts are not yet fully understood. While techniques like continual training and retrieval show promise, they are not without limitations. Future research should focus on deepening our understanding of LLM neural architectures, developing more robust evaluation metrics, and innovating on enhancement techniques. As LLMs become increasingly integrated into our digital ecosystem, ensuring their factual reliability will be paramount, with significant implications for the AI community and beyond. Thank you for watching.